Hello everyone, welcome back. I'm here with another episode of Machine Learning series. So let's get started. Have you ever trained a machine learning model and it gave weird result even though your code was perfect? It might not be your model, it might be your data as a scale. Today we'll uncover why feature scaling and normalization are essential and how they make your models smarter, faster, and more accurate. Let's start with the real-world problem that scaling solves. Imagine we have two features, income and age, and we want to predict whether someone buys a product or not. Income ranges in thousands and age is in tens. So if we feed them into a model like KNN or SVM, the model will think income is way more important, simply because it has bigger numbers, not because it's more predictive, but because it dominates the math. This is where scaling comes to the rescue. Feature scaling means adjusting your numeric variables so that they share a similar range. It's like making sure everyone's voice is heard equally, not just the loudest. In math terms, it ensures that one feature doesn't overshadow others simply because of units or magnitude. Now, there are two main ways to do this: normalization and standardization. Normalization, also called min-max scaling, squeezes your data into the fixed range, usually between 0 and 1. It's great for algorithms that depend on distance, like KNN or neural networks. The formula is simple. X prime equals x minus minimum of x divided by maximum of x minus minimum of x. After normalization, all your features speak the same scale language. But what if your data has outlier or isn't nicely bounded? That's where standardization comes in. Standardization transforms your data so that it has a mean of 0 and standard deviation of 1. It doesn't squish your data between 0 and 1, it centers and scales it. So this is perfect for algorithms like logistic regression, SVM, or principal component analysis, which assume data is centered. In short, normalization works with ranges and standardization works with distributions. So now let's see how scaling affects actual model performance. Here is a KNN classifier before and after scaling. You see, without scaling, one variable dominates distances and the decision boundary gets distorted. And on the other hand, on the right, after scaling, our features contribute fairly, and the model's boundary looks balanced and realistic. So scaling doesn't just make things look nice, it literally changes your model's geometry. Here is the summary. Use normalization when your data has fixed bounds and you're using distance-based models. And use standardization when your model assumes normally distributed features or when your data contains outliers because it's not sensitive to it. Now let's connect this to real machine learning algorithms. Not all algorithms care about scaling equally. Distance-based and optimization-based models need it because their math depends on magnitude. But how about tree-based models? Not really. They split data by order, not distance. So if you have ever wondered why your tree worked fine, but your neural net failed, now you know why. There are some common mistakes when doing these two techniques. Don't scale your target variable. Do only predictors. Don't fit the scalar on your test set. That leaks information. And finally, don't mix methods. Consistency is the key. Now let's wrap up with a quick recap. So here is your takeaways. Scaling isn't optional, it's preparation. It ensures your model interprets data fairly, converge faster, and perform better. And before you tune hyperparameters or stack models, make sure your data speaks the same scale. In the next episode, we'll explore how probability forms the foundation of machine learning and how thinking probabilistically changes everything. So I'll see you in the next one.